So yeah, thanks to the organizers and thanks to all of you for being here for the first talk of the day. I will talk about Parity plaquette compilation. And so first I will introduce the Parity framework as it was originally published and then its extensions over the years. Then I will talk specifically about the problem of plaquette compilation. And then I will make a bit of a shift to Rydberg atoms. So I'll explain, we've heard already yesterday quite a bit about Rydberg atoms. So I'll quickly introduce the platform and then also show how you can use plaquette compilation as a tool to compile to Rydberg layouts. And finally, I will show some preliminary hardware results of running our algorithm then on the Pascal machine. So already 10 years ago, actually very recently was the 10-year anniversary, this paper was published, a quantum annealing architecture with all-to-all connectivity from local interactions. And it's kind of what started our company and also the whole research around it. And so as you can see, it was originally a purely annealing, quantum annealing architecture. And it has this very specific shape of qubits, which are the white circles with the numbers in them. And then you have these plaquettes, which are the blue squares and the red triangles, which are constraints between the qubits. And it turns out that with this architecture, you can encode any QUBO problem. And then you have only these local plaquettes and qubits. And with that, you can solve any QUBO problem. And so the main advantage of this is that you solve the connectivity bottleneck of encoding something on a quantum machine. And later it turned out that you can also use this as a basis for further compilation, as I will show with Rydberg atoms today. And one other special feature is that the whole problem, so all the Jij, are encoded in local fields on the qubits. So whereas in a normal QUBO formulation you have these 2-qubit terms, the transformation kind of puts all of the local fields on the qubits, and then the constraints, the plaquettes, just have to be strong enough that the mapping is satisfied. So I will go in more detail into this mapping later. So as a first highlight, I would just like to mention that NEC actually implemented this annealing architecture in this way, so with superconducting qubits. So they used KPOs, where you can see here one highlighted plaquette, which is then a superconducting parametric oscillator. And yeah, you can see that one plaquette is really then transformed to this 4-qubit interaction that can be realized then with superconducting qubits. And the idea is then to build this architecture, which is what NEC is currently doing, and then solve optimization problems with it. Yeah, so let's go a bit more into detail about what the Parity framework actually does. And here you can see a QUBO problem on the left, which has, in this case, a fully connected graph, so all edges are present. And then we make this mapping where each edge in this QUBO graph becomes a node or a qubit in the parity picture. And you can see this mapping here, which is mapping these parity qubits are here, single qubits, and here this is this product, which is one edge in the graph. And so these plaquettes or constraints that I was talking about before, they can be seen as consistency equations on the cycles in the QUBO graph. So if you look at, for example, this cycle that is highlighted here with the blue edge between 1 and 4, 2 and 4, 2 and 3, and 2 and 1, this is a cycle in the logical QUBO graph. And if you think about the relative orientation of these edges, it turns out that you can make these consistency equations. And so basically the red edge indicates that the qubits are in opposite orientations. So for example, here qubit 4 and qubit 2 are orientated in different ways. And then you get these consistency equations that if you add all of the edges in such a cycle, then you need to get 0 out of it if you take this, this operation, which is often called XOR or direct sum. It has different names depending on how you want to think about it, but it's exactly this condition that an even amount of ones have to be in the cycle. And so then in the parity picture, we need to make sure that we implement not just one of those consistency equations, but exactly enough of them to compensate for all of the degrees of freedom that we introduced. So you can see in the qubit picture we have 5 qubits, and here we have 10 qubits, so we need to make sure that we compensate for all these extra degrees of freedom by adding these consistency equations, which are then the parity constraints. And yeah, again here you can see that whereas here the problem is all 2-qubit edges, now it's only single qubit terms with the JIJs, and then you have these the plaquette terms as the constraints. And it turns out that this also works for higher order optimization problems. So if you have a polynomial problem, which can have these hyper edges, so in general the Hamiltonian can look like this, where you have both 2-qubit terms, but also 3-qubit terms, and in general up to n qubit terms. And every edge here, so it can be a hyper edge in this case, is again translated to 1 qubit in this picture. So for example, the hyper edge 235 translates to this qubit 235 in the parity picture. And yeah, here you can then again see this mapping where a single qubit is the product of many qubits in this original representation. And the conditions work exactly the same. So if you look at this equation, then you need again an even number of ones in this equation to satisfy the consistency equation that they sum up to 0 modulo 2. Exactly. And so the plaquettes here you can again think about them as cycles in the logical graph, but now they are kind of this special form that you want every index to be an even amount of times in a plaquette. So if you, for example, look at this triangle, the 4 is in this qubit and in this qubit, the 5 is here and there, the 2 is there, and the 3 is also there and there. So every logical index occurs an even amount of times in total in the plaquette, and that is basically the same as stating this consistency equation. So that is how the parity mapping works. So it maps an optimization problem, in this case, a higher order optimization problem, to the parity picture with these qubits and plaquettes. And again, you have all of the problem encoded in the local fields on the qubits. And now I would like to talk about compilation. So this was basically a direct mapping, right? So I mean, this is already a kind of compiled example, but if you look at the original LHZ, it's kind of a direct mapping from one picture to the other picture. But if you have any other problem, like this problem where you don't have a fully connected graph, but some of the edges are missing, you can still make the same mapping to this LHZ triangle, but then these gray qubits are ancilla qubits. So qubits, for example, this 0,2 edge, this is an edge that is not present in the graph, so you're only adding it to complete the mapping. And if you could rearrange the plaquettes, which is shown then on this picture on the right, you can get rid of these gray qubits while still satisfying the parity mapping. So I mean, if you would just naively drop all these gray qubits, you would also remove all of those plaquettes that they are in, and then the mapping wouldn't be complete. So what you have to do is rearrange the plaquettes in a way that you still get enough of these plaquettes, but you ideally would like to have no ancilla qubits, or at least as few as possible. Yeah, and so to give you a bit of an idea of how you could do this, again, it starts by finding cycles in the graph. So if you look at this graph on the left, there's actually 5 possible cycles that you could make of length 3 and 4. So there's 2 triangles that you can make, which are these length 3 cycles 1, 2, 6, and 3, 4, 5 on the bottom. And so these cycles translate to the plaquettes that you see here. And in a similar way, there are 3 squares you can make. For example, this 5, 6, 2, 3, 1, 6, 5, 4, and 4, 1, 2, 3. So you have these 5 plaquettes that you can make, and you can now think about these as puzzle pieces. So you need to attach these plaquettes to each other in a way that you have enough of them in the end, and that every qubit only occurs there twice. So as you can see, for example, this 2, 6 is here, and the 2, 6 is here. So if I would want to use both of these plaquettes, I would have to make sure that they attach in that very specific way that this 2, 6 and this 2, 6 kind of overlap. And so here I've shown kind of already arranging the plaquettes in a way that it kind of makes sense. So you have these 3 5s here next to each other, the 5 6s here, the 4 5s here, and the 2 6s here, 1 6 here. And then if you kind of put it all together, you get this picture. And you also get this kind of leftover puzzle piece. So the idea is that this plaquette is also a consistency equation, but this consistency equation is present in this graph, but as a sum of the other equations. So it's a redundant equation. It's something that is already present by having these 4. And you can see that by kind of adding up all of these 4 plaquettes, and then you get exactly these outer corners, which are this plaquette. And so if you add up all of the consistency equations, you basically get the last one. So it's a linear system of equations where you have then one redundant option. And this actually makes the compilation or the plaquette compilation problem hard in general, because in this case we only had 1 leftover puzzle piece, but in general you could have many. So the larger the problem is, the more of these cycles you can find, and so the more puzzle pieces you have. So the puzzle becomes larger, but also the amount of options becomes large. And so in general, what you could do is, and what is kind of the easiest approach, is to just kind of take all your puzzle pieces and just try to arrange them in a way until you kind of stumble into a solution. And you can also try to add some heuristics. So if you think, okay, maybe if I prioritize putting these 2 pieces together, then it becomes a good solution. But in general, this is very hard to scale. So the plaquette compilation is an NP-hard problem. And so if you want to find an optimal solution without any ancilla qubits, this is a hard problem. And as one solution to this, we published this paper last year about constructive plaquette compilation for the Parity architecture. And the idea is now to not look for a perfect solution without any ancillas, but to look for a solution that has some ancillas. So you're basically finding an approximate solution to the plaquette compilation problem. And so this is not the very best arrangement for this specific problem that I'm showing here. So the white qubits, again, are the problem qubits that you want to implement, and the gray qubits are ancilla qubits that you use additionally to complete the mapping. And I think this picture kind of shows the algorithm of how we do plaquette compilation in this example. So the numbers on the plaquettes, they don't represent anything physically. They just represent the order in which the compiler put down the constraints. So just to highlight kind of the plaquette compiler algorithm. And so you start with this plaquette 1, which is in the bottom left corner. And then you want to add constraints in layers. So you always start with a single qubit or a single plaquette. And then you add these constraints in layers. So you pick any square in this case. You see if you can attach anything here, which you can in this case. Then you attach this one here and this plaquette there. And then once you've placed these 4, you've kind of completed the first 2 layers. And then every time after you complete a layer, you move on to the next layer. And so here you have then, again, you try to attach plaquettes in this regular shape, which you can keep doing for a while. Here you can even still add this 10th plaquette to the 4th layer. But at some point you realize, okay, there's actually nothing that I could place here, because this 0.5 qubit is not part of the problem. So if I want to keep making progress, I cannot add anything directly. I need to use something else. And that is where then the ancilla qubits come in. So actually what this 11 series of plaquettes, this is implementing one useful plaquette in total. So you can see it uses these 2 gray qubits. And then if you kind of think about these 3 plaquettes as one big plaquette, that is kind of a stretched out version of what you would like to implement. So actually this, these gray ancilla qubits are just there to kind of connect geometrically the qubits that are too far away to directly put a plaquette. And it turns out that this you can, not just kind of brute force by trying all options, but you can basically calculate how many plaquettes you need in total, and you can then kind of see in your layout, based on where the qubits are already placed, how you can implement any plaquette that you would like as a combination of these kind of plaquettes with ancilla qubits. And so in this paper, we highlight the linear algebra framework that is behind there, and that you can use to find these kind of long-range plaquettes. And basically, so after we've then found this plaquette, which is kind of stretched out in this example, you can keep going in this layer and add here a normal plaquette and another one. This 12 and 13, they are just direct puzzle pieces from your problem. And then here's a bit of a special case where we add this gray plaquette just to fill up the layer. So a big part of this algorithm is that you want to always fill up your layers completely so that you can carry every information to the outer edge. So for example, this plaquette is to ensure that the 3.4 and 4.7 qubits are still available to use later on in the algorithm. So every time you cannot place anything more useful in the layer, you fill it up with plaquettes so that you can keep this, this compact layout where you can always keep adding things to. And then so in the final layer, it turns out you don't need to add anything here anymore, but you can add one more plaquette here and one more kind of long-range stretched out plaquette here, and also one long-range plaquette here. So yeah, you can then, after you find one of these layouts, you can say, okay, this layout is good enough for me. In this case, it uses quite a few ancillas, so like 8 or so ancillas. But you can also keep optimizing. So there's a few choices, of course, like your starting plaquette, but also which plaquettes you attach to it. There's quite a few choices of how to pick at each point your choices. But the nice thing is that any iteration of your algorithm will lead to a successful layout. So it will lead to one of these layouts that has a fixed number of ancilla qubits, and that gives you a really nice place to start from to do the optimization. So you can just keep iterating through your algorithm every time you get some solution with a fixed number of ancilla qubits, and then you can keep going until you're satisfied with solution quality. Yeah, and now I would jump a little bit to Rydberg atoms. So we've already heard yesterday quite a few introductions to it, so I won't be very long about this. But basically you have these atoms which have a low energy or a low spin state and a high spin state, and this Rydberg state is now very highly excited, so that when two atoms are in this Rydberg state, they have this strong van der Waals interaction, which depends r to the power 6 on the distance. And it then turns out that if two of these atoms that are in the Rydberg states are very close together, so closer than this Rydberg blockade radius, it basically energetically prevents them from both being in this Rydberg state when you're looking at the ground state of the Hamiltonian. So we're interested in doing annealing here, so we're interested in the low energy state. And you can also see that yeah, there is then this delta, which increases as you get closer. And so if you now want to implement with Rydberg atoms one of these optimization problems, then this maximum weight independent set is a very natural candidate, because especially if you have this unit disk graph, which means that you have a graph where you have edges exactly if nodes are within a certain radius, and no edge if the nodes are not within a certain radius, then you can natively encode this on a Rydberg platform. And so again, this maximum independent set is a set of nodes which has no connections and the maximum weight. And then the weighted version is that each node has some weight to it, and then you want to find the maximum of this sum of the nodes. And in order to compile this in the Parity architecture, we first have to build up some building blocks. And so the most basic building block is one of these links that we've also heard about yesterday, which is basically this condition of adding two bits to each other, which sums up to 0. And you can do this, for example, in the following way, where you have here your A and B. So these are the NA here that you care about. And then you have this ancilla qubit in the middle, which has a weight 2. So the outside points have a weight 1, and this has a weight 2. And now if you look at the maximum independent sets for this problem, they will look like this. So both of them have weight 2. Either you have a set of these two qubits, which is 1 plus 1, but you can also have a set of just this ancilla qubit, but because it has weight 2, it has exactly the same energy. And so what you see here is that if you look at the kind of truth table, either both of the qubits are 1 or both of them are 0, which is exactly this condition that you want to implement. And you can do this also for longer links if you want, by basically adding two of these smaller links to each other, which means that you get something like this, where A and B are again the outside points, and then then you have either a maximum independent set of A, B, and this middle ancilla qubit, which is weight 4, or these two ancilla qubits, which is also weight 4. So again, either A and B are both part of the maximum independent set, or they're both not part of the maximum independent set, which is exactly this condition that you want to implement. And then if we go one step further, now we have a condition of NA plus NB and C equals 1. So this is now a three-body clause. It turns out that you can implement this gadget using this triangle. And so to see how this works, you have, for example, here again, you have weight 1s on the A, B, and C, so the qubits that you care about. And you have weight 2 on all of the other ancilla qubits. So these three qubits are ancilla qubits. And then it turns out that any maximum independent set you can find here has weight 3. And one example is if all of the A, B, and C are in the independent set, which is weight 3, but also if you have one of the corner atoms, so one of A, B, and C, and one of the ancilla atoms. And then if you look again at this truth table, you see this is the case where A, B, and C are in the independent set, and this is then the case where only C, only B, or only A is in the independent set. And again, this you can see this exactly encodes this condition. Yeah, and it turns out that this way of implementing this condition with Rydberg atoms is optimal in terms of the number of atoms. And now if you want to do a four-body clause, the basic idea is that you add two of these three-body clauses to each other. So if you think about it as a decomposition, you add this NE, which is an ancilla qubit, to your clause. You basically break down this four-qubit clause into two three-body clauses using this ancilla qubit. So the sum of these three equals 1, and the sum of these three equals 1. And if you then add these two clauses to each other, the ancilla qubit would cancel, and you would get exactly this clause. And so this would basically be the version where this E ancilla qubit is in the middle, and then you have two of these triangles, and you can check that any maximum independent set has an even amount of A, B, C, and D involved in it. So you could have the set with A, B, C, and D, and in this case you could add then the ancilla qubit E to it. So this has weight 6, which is this bottom one, but there's also many other ones. For example, the one where none of A, B, C, and D are in, which is then this qubit, and this qubit, which is also weight 6. So you have many maximum independent sets, but all of them satisfy this condition, and also it's a sufficient and necessary condition. So if it's in here, then it's a maximum independent set, and otherwise it's not. So that is how you can encode a four-body class. And what you can do to make it perform slightly better in real life is to add a link to it, so to kind of basically spread out this E ancilla qubit over 2, so that the two triangles, so that this part basically and this part are a bit further away from it. And I haven't really talked about this, but because you have this r to the power 6 relation, the Rydberg blockade is not a perfect step function. It's not like if you have two qubits exactly at the Rydberg radius, the blockade radius, it's a perfect exclusion, and if you have them slightly further away, they don't care about each other at all. Of course, it's a more slow process, so it kind of helps to, for example, in this case, this qubit and this qubit are still kind of close enough to each other that they would feel each other slightly, and so that can then make your runs harder. Which means that if you can spread them out a bit with these links, the performance can become better. So just to recap this part of the presentation, you start with the optimization problem, which can be this hypergraph, so higher order optimization problem. You can then compile it to the Parity language, and we've seen that all of these squares and triangles are these 3-body and 4-body conditions. And basically what you can then do is, like we've seen, the triangle you can convert to this 3-body clause that we've seen how that works, so the 3-body gadget, and the square you can convert to this gadget that we've also seen. And then you have these links which you can use to connect all these triangles and squares. Yeah, and so to see how this will work in practice, here I've shown this layout and how you can implement it with these gadgets. So this square, for example, becomes this thing here, which is a triangle with a link and this triangle, so that is this gadget. And this triangle is actually kind of included in this, because you can think about this square again as kind of two triangles, but then you already have this triangle in there. And then basically here you have this link then to this triangle. And this is a bit of a special case, because if you have like a triangle like this and a triangle like this, so this comes from these two sitting on top of each other, you can kind of squeeze them together, and it turns out that it's better to do this, which is this kind of diamond shape, than to do two triangles with links between them, because they are kind of, they would have a lot of crosstalk, which will make it behave worse. And then, on this side you have, this is a square, and this is a square, exactly like put together again in this diamond shape. So that is the right side of this picture. Exactly. And so if you now look at an example of a maximum independent set on this layout that is in this red atom. So for example, here the 4 outer qubits of this square are red, which means that these would then be in the up state in the corresponding parity picture. And so you can see basically that in these links, every second atom is always in the independent set, because then it kind of carries over really this qubit is exactly always in the same state as this qubit, so that you can use to link up the different parts of the layout. Yeah, and then there's one more extension you can make to this framework, which is to use anchor atoms. So these are very special atoms, so you always put them outside of the blockade radius of all of the other atoms. And so, for example, this blue atom here, it's not blockaded by any of the other Rydberg atoms, but it's still close enough to some of them that this van der Waals interaction still influences them. And it turns out that this has a nice advantage because you have this degree of freedom of where exactly you put it. So you can put it slightly up, slightly down. You can also like vary a bit these distances on a link. And so you have these kind of degrees of freedom to play with. And you can actually use these to compensate for other crosstalk that you get from, for example, qubits that are outside of the Rydberg radius that are too close to each other. So they still feel each other, they're not blockaded, but they still feel each other. And so that is how you can use these extra anchor atoms. You can compensate for the unwanted crosstalk from some of the other things. But you can also do something else which is very interesting, which is reduce the hardware requirements. So if you are smart about this placement, and all the details are in this paper, quantum optimization with globally driven neutral atom arrays, if you're really smart about the placement of all these things, you can actually also add these anchors here. So these are also additional qubits that are outside of the blockade radius. You can drive everything with a global field. So you don't need individual local fields to address every of the single atoms. You can have one global field, which is on the whole layout. And just by placing all of the atoms in exactly the right spots, you can implement any Jij interaction into the atoms. Yes, and so I would like to show you some hardware results. But before we go into detail about the plots, I would just maybe show how, for example, one plaquette here, where now you have your Jij, which are in the parity picture, they are local fields. So you have one square in this example, and the fields are 1 on 3 of the qubits and -1 on the last qubit. And if you translate this again to the Rydberg picture, you get this kind of this gadget that we often saw. So it's a triangle with a link and another triangle. And here these yellow atoms are the anchor atoms that you use to encode also the problem. And so you can see that if you, I mean, it's maybe hard to see, but this atom is slightly further away than the other 3 atoms, which means that this atom kind of helps you encode the -1, which is different from the 1, 1, and 1 that are kind of on the outsides here. And so this atom here is just there to compensate for some of the crosstalk, but these 4 outer atoms are actually implementing the problem fields for this example. And so we ran this gadget on the Pascal hardware. And so these are very preliminary results, so they're not published yet, but we hope to have a paper out in the next months. But you can basically see that, so there are now 3 different states in these graphs. One is the target states. So those are the states that satisfy your Jij, so that are the ground states of the optimization problem. The blue states are logical states, which means that they satisfy the encoding. So they are maximum independent sets in the Rydberg picture. And the gray states are other states. So that could be states that are not a maximum independent set. And then you have this problem encoding factor, which is basically how you rescale the local fields. So if you have your Jij defined to 1, you of course always have this freedom to rescale all of the local fields. And it turns out that this is kind of an important parameter because it really affects how the energy landscape looks. And so it's expected that based on this problem encoding factor, you would just get good energy separations or bad energy separations. And you can see that basically if you have this encoding factor to 0.01, then here you can see the counts, so the most likely states. You cannot really see the orange states showing up as the best states, but if you then look at this one, and especially also this one, you can see that for this problem encoding factor, the 4 most likely states are exactly the target states, so the ground states of this degenerate Hamiltonian. And then if you make the problem encoding factor even higher, then it again becomes worse. So there's this sweet spot, which is the problem encoding factor, where where it works the best. So yeah, this is a small example of how to implement a single plaquette with then the 4 ground states showing up as the most likely outcomes. Yeah, and so to conclude, plaquette compilation is a flexible tool for quantum compilation. I've showed the example of NEC and also now the Rydberg implementation, but there's many more examples where you can use plaquette compilation. For example, also in digital quantum computing, like quantum error correction, but also QA/OA, there's a strong reason to use this plaquette compilation because it really helps you to find a local layout where the connectivity bottleneck is solved by doing the parity compilation. And so if you're interested to talk about any of these topics, I'm happy to talk about it later as well. And one more point maybe is that the ParityQC is a software package that contains our plaquette compilers, also the Rydberg compilers. And yeah, if you're interested to work with this or to do some compilation from there, you're always welcome to reach out to us. So with that, I would like to thank you for your attention and happy to take questions.
Yeah, Paul, go ahead.
Very nice talk, Roeland, thank you. So when you first introduced your parity method, which I think was slide 5, there's an implicit assumption here that your edges are in 0 and 1, but in general you might want fractional values of your edge interactions. Is that possible with this framework?
So the edges are, I mean, you can have any Jij value on the edges, right? Which is in this Hamiltonian, just this coefficient in front. But it's then moved to the local fields, so the Jij on the qubits. So you can have any value on the edge, which is moved to the local field on the qubit. And so these equations, the zeros and ones, they are more about the relative orientation of your spins. So for example, if qubit 2 is spin up and qubit 4 is spin down, then this would be 1. So if they're like in opposite directions, then you have spin 1 in your parity picture, and if they're in the same direction, you have a spin 0 in the parity.
I misunderstood, but I'll ask you more about that in the interval. Thanks.
Okay.
Thanks.
All right, other questions? Anna.
Thanks for the really nice talk. I had a question out of curiosity. When you were explaining the constructed compilation algorithm, do you also have a way, because in the first example that you showed, you didn't use all the plaquettes, right? Mm-hmm. But I take it that here you do try to use them all, or you just complete, so what is...
Yeah, so you never really have to use all of them. It's more that what you can do here is basically like pick a fixed basis of the constraint space. So it's always, you can always think about it as a set of linear equations that you can then also take row operations on to kind of modify which ones you have. And so you can here pick a fixed set of these constraints and find these non-local ways to still implement those constraints. And if you would do that in the other picture, you just have these single plaquettes and at some point you would realize that you cannot attach them to each other anymore. So it's a bit of a different way to think about the same problem. But yeah, you also in this picture, you always have many more options for plaquettes than you can use, which is one of the reasons why you would then do this this optimization, where you would find many layouts and try to find the best one. And
Thanks.
Further questions? We started a little bit late, so we have time. If not, I have actually two. Like in the slide that was titled the example layout, where you showed like the yeah,
this one, first one.
yeah, that one exactly.
Yeah.
So that this type of contraction reminded me intuitively out of like tensor networks. So is there like a unique way to do these type of contractions, or do we also run into similar issues as with tensor networks?
So there are actually, if you just think about the kind of plaquette layout, there are not so many of these cases that come up in this case. So this is actually the kind of only example of where a contraction is useful, with this kind of these two triangles that have this edge that are facing each other. In any other case, it's better to spread everything out more in order to avoid this crosstalk between Rydberg atoms. But you do have sometimes some options about how you link things. So in this picture, you don't run into too many conflicts, but in general, you want your links to go orthogonal out from your gadgets. Because if you would, for example, make a link which goes horizontally this way, it would have too much interaction with the rest of the gadgets. So you want to kind of make your link straight out, which sometimes can lead to conflicts if you have a specific layout of plaquettes. Yeah.
Okay, yeah, thank you. Maybe Axel, you can already set up, and I have one more tiny question, namely the anchor atoms that you place.
Yes.
You place them in like specific distances, right? Because you want a particular interaction strength, I assume. In that case, if you run it on the device, do you then run into issues with like fluctuations of the atoms?
Yeah, so there's always all of the Rydberg atom devices, they have some resolution of like how precise they can put their atoms. And I guess they're also not completely stable. So there are definitely a few challenges that you can again then try to find solutions for. But yeah, the picture here is relatively simple mathematically. Of course, you have to solve all these equations, which is some work. But then if you run it on real hardware, you run into some other issues. Both of the imperfections and noise, and also the resolutions of where you can place atoms.
Okay, yeah, thank you very much. Then let's thank Roeland again.